Lesson 79 is about complex numbers, and first we'll be learning about something called the Moyers Theorem. And if you recall in Lesson 64, we learned how to multiply complex numbers that were in polar form. For example, we learned how to multiply 2 cis of 30 degrees. Remember that cis, that's the polar form of a complex number. Instead of saying 2 angle 30 degrees, we write 2 cosine plus I sine. That's what that cis is abbreviated for. We wanted to multiply 4 cis 30 with 4, 2 cis 30 with 4 cis of 50. We would multiply the magnitudes together. The 2 and the 4 would be an 8, and we think of those as the absolute values, and add the angles together. So we'd end up with 8 cis of 80 degrees. We showed why that works in Lesson 64, so if you don't remember why that works, you might want to go back and review Lesson 64. Now let's understand how de Moyers' theorem works by applying what we know about multiplying complex numbers in polar form. For example, let's say we had 2 cis of 30 degrees, and we multiplied that by the same thing, 2 cis of 30 degrees. We would end up with 2 times 2, or 2 squared, times cis of 2 times 30, right? Likewise, if we had this, 2 cis 30 times 2 cis 30 times another 2 cis 30, we'd end up with 2 times 2 times 2, or 2 cubed cis of 3 times 30, or 90 degrees. So do you see the pattern there? That if we repeatedly multiply a complex number by itself, we get this pattern to develop, and we could just say that if z was equal to r cosine, not cosine, but cis theta, then z to the power of n is going to be equal to r cis theta to the n, which we can just change to r to the n cis n theta. That is called de Moyers' theorem, and that was developed by a French mathematician, Abraham de Moyers. He was a refugee to London. He lived in the 1600s, late 1600s, early 1700s, around the time of many other famous scientists and mathematicians, such as Isaac Newton. Let's go ahead and apply what we've learned here about de Moyers' theorem. In A, let's find 3 cis 20 degrees to the 4th power. Let's simplify that, is what we need to do there. And we'll use de Moyers' theorem to do that. We'll just say that that is equal to 3 to the 4th times cis of 4 times 20, or 80 degrees. And so we'll end up with 81, because that's what 3 to the 4th is, 81 cis of 80 degrees. There's an application of de Moyers' theorem, simplifying that relationship. Let's do another one. Look at this problem. Find the square root of 3 plus I to the 12th power. Now, you might think, oh, I need to use Pascal's triangle and expand this out. But there's a simpler way to do this. What we can do is use de Moyers' theorem, convert that to polar coordinates first, then use de Moyers' theorem and simplify that expression. Then we can rewrite it in rectangular form. So first of all, let's just kind of think about how to write this in polar coordinates. Let's just write a Cartesian coordinate system. Think about where we are. We go to the square root of 3 to the right, and then plus I. That would give us a 30-degree angle, right? So this is really like saying a magnitude of 2 cis 30 degrees to the 12th power, which would be 2 to the 12th cis of 12 times 30, or 360 degrees. 2 to the 12th is 4,096. So we'd have 4,096 cis of 360 degrees. Now to rewrite that in rectangular form, we'd say 4,096 times cosine of 360, which would just be 1. Cosine of 360 would be 1, and so that would be 4,096. And then 4,096 times I sine of 360. Sine of 360 would be 0. So that huge expression, if we did that using even a simplified form such as Pascal's triangle, that would have still been a difficult problem to work on. Here's our answer, 4,096. We just found it in basically a couple of steps. So as you can see there, the Moyers Theorem is very helpful in simplifying some large, or possibly very large, mathematical expressions. Well, let's go on to part B on the roots of complex numbers. In order to understand what we're trying to do here, let's just think of roots of real numbers, or whole numbers is really the simplest way to start. Let's say we had the square root of 4. The square root of 4, that means we'd have plus or minus 2, right? Both of those work. Those could both be roots of the square root of 4. Remember, a radical sign by itself, that also means 4 to the 1/2 power. So the two roots of 4 to the 1/2 power are plus and minus 2. Now let's try this one. The cube root of 8. We think of what times what times what would equal the cube root of 8, and that would be a 2. 2 is the cube root of 8. Now, how come we had two answers on the square root of 4, but we only have one answer for the cube root of 8? The reason is the other answers for the cube root of 8 are complex numbers, and we haven't really figured out how to find roots of complex numbers before. So for any number to the, basically to the root of n, there are n roots. For any number to the power of 1 over n is really, I guess, the best way to think about that, because that's what that radical sign means, is 1 over. For any number to the power of 1 over n, there are n roots. So a square root problem should have 2 roots, a cube root should have 3 roots, a fourth root should have 4 roots, and so on. So how could we find those other 2 roots of the cube root of 8? Well, let's just think about how we could write the cube root of 8 in complex form. We could just say 8 to the 1/3 power cis of 0 degrees. Let's start with just the 8 itself. 8 cis of 0 degrees. And think about that 8 to the 1/3 power cis of 0. Think about de Moyers Theorem, r to the n cis of n theta. If we apply that to what we have written already, 8 to the 1/3 power cis, we'd have cis of 0 over 3. And this would simplify to 2 cis of 0 degrees. Now think about 2 other values that would work for this relationship. What you have to do on problems like this is just kind of work in multiples of 360. If 8 1/3 cis 0 over 3 is what you start with. We'll start with 8 cis 0 degrees, and then think of 8 cis of 360 If you substitute that, basically what you're doing is using the Moyers Theorem again. Say 8 1/3 cis of 360 over 3. You would say 2 cis 120 is the answer. And then go one more time, do 8 cis 720. You would have 2 cis of 240 degrees. I mean, you could keep going on this, but the way that you're supposed to think about it is for any number x to the 1 over n, basically there are n roots, n distinct roots. Because see, what would happen here is if we did another lap around and added another 360, we'd have 2 cis 360, which is the same thing as 2 cis 0. We'd be back at the beginning again. So these are our 3 roots. Let's think about this and let's try to prove that is true. Let's just take 2 cis 120 just so you can see that this really does work and you do get another root. 2 cosine 120, that would be basically -1, and then 2 sine of 120 would be a positive square root of 3. So that's the complex form of 2 cis 120 form. Now let's cube those, and this should get us back to 8. If that is really a root, if 2 cis 120 is a root of the cube root of 8, multiplying that out 3 times should get us back to 100. I'm sorry, it should get us back to 8. Let's just think about Pascal's triangle to expand this out. We'd have a to the third plus 3a squared b plus 3ab squared plus b to the third. So a is -1. We'd have -1 cubed would be -1 plus 3 times -1 squared times b. That would give us a positive 3 times the square root of 3i. And then the next thing we'd have is 3ab squared, so that would be 3 times a -1. That would be -3 times the square root of 3 squared, which would be positive 3. But there's that I in there. We're doing square root of 3i, so it actually ends up being -3. Why don't we write all that out? It would be 3 times -1, and then times the square root of 3i. That squared would be a -3. And then plus b cubed. Square root of 3 times square root of 3i would be -3. And then times another square root of 3i. So the I terms cancel, and we have -1 plus 9 equals 8. So that did work. Let's just go back through and kind of think about what we did here to find the other roots for the cube root of 8. The first thing we had to understand is for any number x to the 1 over n, there are n distinct roots. And what we did was we took 8 and we just said 8 cis 0. We wrote it like it would be in polar form for a complex number. Then basically what we did was use the Moyers Theorem to figure out what some of our roots would be. We just said, well, 8 to the 1/3 cis of 0 over 3. Basically what we did was we took the cube root of this and then applied the Moyers Theorem to it. 8 to the 1/3 cis 0 over 3. So we found that one root was 2 cis 0 degrees, which would just end up being 2. And then we just kept going around in multiples of 360 until we had all 3 of the roots for that particular number. Let's go ahead and do a practice problem. Let's find the 3 cube roots of 27i. Well, first, what we ought to do, just like we did when we were looking at the number 8, is write this in complex form for a polar number, or polar form of a complex number. Think about that. It's the same thing as 0 plus 27i, isn't it? So we could say 27 cis of 90 degrees. Hopefully you see why that would be, because cosine of 90 is 0. I sine of 90 would be 1. 27 times that is 27i. Now we want the 3 cube roots of that number, or in other words, that number to the 1/3 power. Use the Moyers Theorem backwards now. And let's find the first root. It would be 27 to the 1/3 cis of 90 over 3. 27 to the 1/3 power, the cube root of 27 is just 3 cis of 30 degrees. We know that we have to have 2 more roots, because for every problem like that to the nth power, 1 over nth power, there will be n distinct roots. So what we need to do is add 360 to 90. 360 plus 90 would be 450. Divide that by 3. We should have another root at 150. 3 cis 150. And what you can see here is that your multiples are always 360 over n. So n is 3 in this case. 360 over 3 is 120. This next one will be 3 cis of 270. If we added another multiple, we'd be at 390, which is the same thing as 30 degrees. So that's our 3 roots right there. Get your number in polar form for a complex number, and then just raise it to whatever power you need to. Apply de Moyers theorem backwards is really what you have to think of. Z to the n is equal to r cosine I sine theta to the n, which is equal to r to the n cis of n times theta. Here, our n value is a fraction, so like we have cosine I sine n theta, if n is 1/3, it ends up being theta over 3. That's why we have the fraction. So it's kind of like it's backwards because we're using 1 over n instead of n. But it's the same idea. Get your number in polar form for a complex number, then apply de Moyers theorem. It'll kind of seem like it's backwards, but it really isn't backwards. It's just that you have a fraction for n instead of a whole number. And then for your angles, just think about this. For angles, add 360 degrees over the number of roots for each new root found. So that's kind of one way of thinking, just maybe making a simplification here. You find 3 cis 30 in this problem. You add 360 over 3, since there's 3 roots, or 120 for each new root. So you'd have 3 cis 150, 3 cis 270, and then you're done. Okay, well that's all for lesson 79.